And for some reason, we went back there. All right, we are now recording. If we can get PowerPoint to open, there we are. Okay, let me just say this. I'll try to say this every class as we go now. This, obviously my best class in that 3 people have turned in research papers so far. But that's 3 out of 15, and we only have a couple of weeks left. Okay, so please, folks, get your research papers in.
Did you say we can email those to you?
I'm sorry?
Didn't you say we can email those to you?
You can, but I grade what I receive. So unless you're absolutely certain it's in the format and it looks like you want it to look, whatever I get, that's what I have to grade. So it's up to you. The first test. This class has been pretty good about that. I'd say well over half of you have turned that in, but there's still quite a few who have not. 1, 2, 3, 4, 5. A third of you have not turned it in yet. Test 2, several of you have. I graded several over the weekend. So I've got 1, 2, 3, 4, 5, 6, 7. Almost half the class has not turned that in. Just over half have turned in test 2. And I'm giving out test 3 today. So please, folks, get caught up. This is getting too near the end of the term to be that far behind. No research paper, no first test, no second test, and you're about to get the third test. That's really putting yourself in a bad situation. Of course, I'm probably preaching to the choir here. Y'all are probably right up to where you need to be, but that's why I wanted it on Screencast-O-Matic, because some of you are not anywhere close to where you need to be. All right. Commercial over. Any questions on anything we've covered so far? All right, we're talking about Newton's method. It said it can be shown that a condition sufficient to produce convergence of Newton's method is Newton's method to a 0 of f, okay, is that this thing has to be true. The absolute value of your f of x times your f double prime of x divided by f prime squared, okay? If that is less than 1, it will converge, okay? That's on an interval containing the 0 of that function. So what you have to do, which you have to do anyway, you know what the function is, you know what the first derivative is, you have to have that for Newton's method in order to determine, well, you don't have to have it, but if you're talking about how close you're going to get, you're going to need the second derivative as well, and that's important because, remember, one of the last things we talked about, well, I thought it was earlier. Oh, man. Okay, I can't see it now. It was that last example. Maybe it's just things that we had observed about it. Let's go back to that. That last example here, we know it's not going to converge. Well, part of this reason is that the value at 0 is not defined, okay? But you're not at 0. You're to the right of 0. But your first iteration takes you back on the other side of 0, and you've gone across. Now, the function is defined there, but the first derivative is not defined at 0, but this takes you back and forth. Now, I think I pointed this out to you. Part of the reason is because it's curving the wrong way. And the curvature, that's based on the second derivative, okay? So we had talked about that in general, but hadn't done anything specific. And that's why, following that, we see this. That second derivative is of crucial importance here, okay? But you would think with the absolute value, you've lost the indicator of whether it's going the wrong way or not, but it's the product. Well, it's still, the second derivative is important here. Okay? So you have to take one more step, do the second derivative, and then compare this at the point, at the value for x that you're trying to find a 0, okay, and see if that comes up less than 1. If it does not come up less than 1, don't even try, okay, because it's probably not going to give you a 0, okay? You have learned several techniques for finding the zeros of functions. The zeros of some functions, like this one, can be found. What would you do with one like that?
Take the derivative, but that's when
You could, but actually to find the 0,
take out.
group it, and then factor by grouping. You can find the zeros without taking a single derivative, because that happens to work, okay? Factoring by grouping is that, okay? This one right here, no way to factor that I know whatsoever, okay? Cannot be found by the factoring or some other elementary algebraic method, so this one, Newton's method, okay? And your first step is to take a derivative, like you said. But there's sometimes you can find the zeros without. Okay? This particular function has only one real 0. Now, do we know that, like they say, a priori? Okay? Well, remember Descartes' rule of signs. That tells you you can count the number of zeros by counting the number of sign changes. Well, here you have one sign change and a second sign change. So this has either 2 or 0 positive real zeros. And then to get the negative real zeros, consider alpha minus x. Okay? And that would be minus x cubed plus x plus x plus 1. Well, then that would be minus, plus, that's one change, and plus plus is not a change. So there's only one negative real 0. Okay? You know you got that one. Okay? But it still doesn't tell you whether you have 1 or 0 positive real zeros. It looks here and says this particular function has only one real 0. That's a negative one. And by using more advanced algebraic techniques, you can determine that 0 to be this thing. Oh, yes, of course, we wanted to do that. That's a mess, isn't it? Okay? But because the exact solution is written in terms of square roots and cube roots, it's called a solution by radicals. Okay? That's advanced algebraic techniques for sure. Okay? And that is the one and only one. And notice it's negative. Because whatever this is in here, well, let's see, can we guarantee that? The square root of 23 over 3, that's a little bit more than the square root of 7. Square root of 7 is less than 3, right? So 3 minus that, that's going to be a positive number, and that's positive, so this is going to make it negative. Now, this one, square root of 7, whatever that is, added to it, it's going to be positive. And you're subtracting that. So this is obviously your one and only one negative square root. Okay? Because the exact solution, okay, right, we already read that. Okay? So there is your one and only one negative square root. The two that would have been positive turn out being complex. Okay? You can't prove that here, but it is the case. Now, that's all she wrote. Now, what you can do is graph that function, this one right here, and on a graphing calculator and see what you get. And sure enough, it's going to have a 0 here, and then over here it's going to go up and down, but not cross the x-axis again. Okay? Now, let's go back to example 1. Okay? F of x is equal to x squared minus 2. Okay? Let's find some screen to write on. I guess that's going to be about the best. This might be good. So, whoa, I forgot to change my pen. Okay. F of x is equal to x squared minus 2. Okay. We know it has two solutions, right? We already did this problem before. Okay? But let's use, in fact, let me go back. Let's just use this. It's not going to take that much room. All right. F of x is equal to x squared minus 2. Okay? Now, in order to use this condition here, what else do we need to know? First derivative is 2x. And what else do we need to know to use this? Second derivative is? Is what? Help me?
I said 2x. I said it
Huh? What did you just? I couldn't hear what you said.
I was saying it was going to be 2x, but I said
Not 2x, but it's pretty easy. What is the derivative of 2x? No. Derivative of 2x. Derivative of x would be 1. Derivative of 2x would be 2. Okay. All right. Yeah. Okay. You take the exponent 1, multiply it by the coefficient 2, reduce that by 1, that becomes x to the 0, which is 1. So 2 times 1 is 2. Okay. Now let's use our test here and do the absolute value of, okay, where are we evaluating this? Well, we don't need to worry with it. Let's just do it. F of x would be x squared minus 2 times f double prime is 2 divided by f prime 2x, but square it, and you get the absolute value of 2x squared minus 4, right, divided by 4x to the 4th, right? And the question is this less than 1? Okay? Now, let's break this off into 2x squared minus 4, no. Okay, 2x squared over 4x squared minus 4 over 4x squared. Okay? And that would equal, I could have simplified a little bit more earlier, absolute value of 1/2, right? Minus 1 over x squared. Okay? Now, the question is that less than 1? All right. Now, no matter what value you choose for x, now you can't choose 0, obviously, right? X cannot be 0 and doesn't make any sense, okay? But even if x is very close to 0, well, let's see. Yeah, ooh, we got problems near 0. Anything less than, okay, obviously when this is the square root of, let's just say 1, let's just say x is 1, then we got a problem. Well, no, we don't. Sorry, forgot about the absolute values now. If that is equal to 1, then this is 1. 1/2 minus 1 is 1/2. Okay? That's less than 1. Let's say x equal 1/2. That would be 1/2 minus 1 over 1/4, right? And 1 over 1/4 is 2. And x minus, or 1/2 minus 2, minus 4, would be a minus 3. Absolute value of that is 3. That's greater than 1. So for any x's between, and it's actually between you have to do some sort of work on the arithmetic here, but for any place where x is not too close to 0, this is going to work no problem. 1 and greater, -1 and greater, actually 1/2 won't work, but somewhere there you'll have values that will work. Okay? Now, how do they deal with that? Okay? On the interval 1 to 3, for sure, that quantity is less than 0, and that may have been our example 1. Well, they use x equal 1 as a value. Okay? Now, if you go back to the illustration from example 1, now let's see if they show that. I don't think they do, but let's see if they do. There it is. Okay? Obviously, x equals 0 is not going to work because your derivative is 0. Horizontal line, you can't divide by 0 anyway. That's not going to get you a solution. If you're close to 0, though, there's your first guess. Okay? And, well, let's say your first guess was in here. That's going to take you way out there somewhere. So you have to get past the place where, and this is where that second derivative comes in. If the second derivative is too small, then this isn't going to converge for you. But anything, even here, is going to probably work for you. There's some point in here, past that, it's not going to give you a solution. But if you do anything from 1 and beyond, that's going to work. Even, I think, 3/4 might work. Let's see what that would be. Yeah, let's not get into it now. But that's certainly anything from 1 and out is going to work. And if you show the other half of the parabola, -1, and beyond that, negatively, that's going to give you your solution. This, however, in here, right around 0, will not. Okay, 0 obviously won't. Anything close to 0 will not as well. Okay? Okay. So let's go back to where we were. There. So, as I say, on the interval 1 to 3, that quantity is less than 1, therefore the convergence is guaranteed. On the other hand, in example 3, now let's go back to, well, let's keep this here. Erase all this. Okay? Example 3. That's the one we just did that is not going to work. F of x is equal to x to the 1/3. And then what do we do next? What else do we need here? F of x is x to the 1/3. What's f prime? 1 over 3 x to the -2/3. Right. Okay. And we'll also need f double prime. And that's going to be -2/9 x to the -5/3. Okay. Let's try our technique there. F of x, which is x to the 1/3, times f double prime of x, which is -2/9 x to the -5/3, divided by f prime squared, which is 1/3 x to the -2/3 squared. Okay, what's that going to be? Well, in your numerator, you're going to have a negative 2/9 x to the, subtract the 1/3 from the 5/3, negative, 5/3, or you're adding them actually, but since they're different signs, it's a subtraction. That would be x to the negative 4/3 over, and when you want square 1/3, you get 1/9 x to the, when you square a power, you basically are doubling that, so that's going to be a negative 4/3. Okay? Hey, look at that. Your x's to the negative 4/3 are going to disappear, and what do you have here? The absolute value of and your 9's will cancel out. You have the absolute value of negative 2. Okay? And the absolute value of negative 2 is 2. Guess what? At absolutely no value for x, will that ever be less than 1? Okay? 2 is never going to be less than 1. So this one does not converge. It doesn't converge near 0. It doesn't converge anywhere. Anywhere at all. No value of x will make that converge. So don't even try. That's one Newton's method will not work on because of this rule right here. Okay? All right. Now, the rest of that is things we've already covered on the slideshow. They do have on the side here 2 young guys. The paintings, I think, are not all that great. Maybe that one, Everis Galois, did look that sneaky. I don't know. But awfully young-looking guys. And when you look at their dates, they Niels Henrik Abel, or however you pronounce that, only lived to be 27 years old, and Everis Galois only lived to be 21. So, although the lives of both Abel and Galois were brief, their work in the fields of analysis and abstract algebra were very far-reaching. You wonder, what in the world could have come out of these two if they had lived normal lives, lifespans? Okay. Actually, normal lives would work for at least one of them, too. Let me see. Dakota came in, and Daniel came in. I get to talking and I'll forget to mark this. Okay. Good deal. All right. The reason I say this, I don't know much about Niels Henrik Abel, so someone could use him as a paper topic and I'd learn something, okay? I've read about Galois before. Evidently, 21 years old, he was full of himself, and he was obviously an extraordinarily bright kid, a young man. But he was so full of himself that I believe he was having an affair with a married woman. Stupid, okay? And as a result of that, got challenged to a duel and stupidly accepted the challenge and died. What was this? Yeah. Yeah. And I don't know what happened to Abel. It may be he died of tuberculosis or something that might he not had any control over. Galois could have had some control over his. He chose not to. Okay, sorry. But anyway, both brilliant mathematicians, though they died at very young ages. 2 potential paper topics. Now, I was saying before, for folks who just came in, it's worth saying again, because you may not go back and listen to the first part of this, I have only received 3 research papers from this class, and we've got this week is week 9, next week is week 10, and then basically final exams. I think we may have class that Monday of the following week, but we just have we have basically almost less than 2 weeks now to go. please get your papers in. That means you only got 2 weekends to work on it if that's when you work on it. Also, from some of you, I've not received test 1, and I've not received test 2. And in just a few minutes, I'll be giving out test 3. So please get the test in as well. Okay? Now, homework exercise, that was, by the way, the end of section 3.8. Here's the homework exercises. Either 3 or 5. They're both at calcchat.com. Also, the answers in the back of the book. But the worked out solutions are at calcchat.com. Number 3 is also more detail is given at calcview.com. Okay? Do any of the odds 7 through 15? All those answers in the back, they're all worked out at calcchat.com. Number 9 is worked at calcview. Do either 17 or 19, they're both in the back of the book and at calcchat. Do 21, it's in the back of the book in calcchat. Then do 23. It's in the back of the book, it's at calcchat, and it's at calcview. Okay? Then do any of the odds, do 25, it's a calcchat in the back of the book. Try 27, it's an exploring concepts one that might take a little more effort, but give it a look. Then do either 21, 29, or 31. They're both at calcchat, neither at calcview. Then do any of the odds 33 or 35. They're both at calcchat in the back of the book. And then there's a true false 39, 37 or 39. They should be at calcchat as well. I assume that 41 will be there too. That's getting a little more esoteric, but you're certainly welcome to do that if you choose. All right. Any questions? 3.8. Let's move on to 3.9, which is the last section in the chapter. Okay? And it's not a very long one, so hopefully we'll get it done today in fairly short order. I don't know what happened to... There we go. 3.8. So here's 3.9. And I should have told you all this first, and it's not a major thing. Hopefully it won't happen. But I think I ate something over the weekend that sort of disagreed with me. Yesterday I was able to function and everything, but the stomach is not right, and this morning it's still not quite right. So if suddenly I say, "Why don't y'all take a break?" I've got to run down the hall. But hopefully that won't happen. But it's better today than it was yesterday, but still having some issues. Sorry to bring that up, but I did want to warn you in case you think, "What's wrong with this guy?" We won't go into detail. All that. Okay. Chapter 3, still applications of differentiation. 3.9, the last chapter is called differentials. Does anyone know what differentials means as opposed to derivative? No. Okay? That's what we're going to get at. We're going to first understand the concept of a tangent line approximation. Wow. Going back to that, huh? Then we'll compare the value of the differential dy with the actual change in y, which is your delta y. Okay? So that is a clue of what a differential is. Obviously, they have to define it first. We'll estimate the propagated error using a differential as opposed to the actual change of y, and we'll find the differential of a function using differentiation formulas, which basically you'll see derivatives, differentials, they're closer than first cousins. I mean, they're almost the same thing. So let's start with the tangent line approximation that we have done, it seems like already, but let's review it. Consider a function f that is differentiable at some value c. The equation for the tangent line at that point, c f of c. Obviously, if the point c is on that function, f of c is the y value. If c is the x value, f of c is the y value. It's on the function. There's a point. The derivative there, we said it's differentiable there, is f prime at the value C, that'll give you the slope at that value. So from the point slope formula, y minus alpha c, that's y1, is equal to m, which is f prime of c, times x minus c, x1. Okay? That is your equation for the tangent line, right? Okay. Now we're going to do ever so slight change to this. We're going to add f of c to both sides. Right? That brings it over here. So y is equal to f at c, that's your y value there, plus the slope change x minus c. So as long as x is not far off from c, this is going to be a small amount. Multiply it by that, that gives you a little bit of a change there. Add it to this, that's a new estimate for the y value. Okay? That is called the tangent line approximation, or the linear approximation, because this is a straight line, okay, of f at c. Obviously, the function f is probably not linear. It could be doing all sorts of things. But the linear approximation would be just a little bit beyond where x is, then you can estimate a new y. Not going to be exact, but it's going to be pretty close. Now, because f is constant, y is a linear function of x, this approximation, whereas the function is probably not a linear function. It's more than likely curvilinear, which means it's changing a little bit differently than this is. Okay? So, moreover, by restricting values of x to those sufficiently close to c, the values of y can be used as approximations to any desired degree of accuracy of the values of the function of f. In other words, as x approaches c, the limit of y is f of c. Yeah, that's what your your equation is telling you. Okay. Now, here's example 1. First, let's find the tangent line approximating f of x is equal to 1 plus sine x at the point 1, 0. Time out, folks. Being the cynic that I am, I want to make sure that this point's on this curve. Is it? X is 0. What is sine x? What is sine of 0? Second? Some of you, I know who you had for trig, so you better know the answer to that. What is sine of 0? Come on, trig majors. Remember how a sine function looks? At 0, it starts and goes up. What's the sine of 0? 0. Okay. You're like a dentist here, pulling teeth. So 1 plus 0 is indeed 1. So f of 0 is indeed 1. So there's a point. It's on the curve, and it says find the tangent line approximation of that function. Okay. At first I said tangent line. We're doing the approximation. Okay. So let's. Oh man. All right. So what do we have to do to find the tangent line approximations? Hint. There it is. Okay, so what do we have to do? I got to get my color back. Okay. Anybody? What's the tangent line approximation? It was a long time ago we did that slide, like 3 minutes. What was the tangent line approximation? There it is. You see it? Got it? Everybody? Okay. Now what's the tangent line approximation? Or did you need more time with it?
F of C plus.
Second?
F of C.
f of c, okay, you got y is equal to f of c plus f prime of c x minus c. Okay? So in our problem, what in the world is c? It's the x value at that point of tangency. And what's the point? It's given here. 1's a number. Second? Okay. 0, 1 is the point. What's the x value of that point? 0. Okay? That's x, that's y. Okay, right? The point is 0, 1, and the c would be 0. So, y is equal to, and what's f of 0? It's pretty easy. We just did it, didn't we? There is the point, 0, 1. What is the y value, f value, at when f is 0? 1. All right, that's 1. We did that earlier, okay? Now, we haven't done f prime of c, so that's what we've got to do. What is f prime of x first? What would that be? Second? Okay, f prime of x is not going to be a number. It's going to be a function of x. Take the derivative of f there, and what do you get? Okay. Derivative of 1 will be 0. That part I'll agree with. What's the derivative of sine? Say again? Okay, I know who your Cal 1 teacher was too. All of you. That's this class. We did derivative of sine. What is it? Help me, somebody. It is cosine.
Yeah, I was trying to see who was like negative cosine.
I know, you're waiting for me to respond, see which one it was. It is cosine. So we want f prime at c. What's your c? Well, you just answered it. Oh my goodness. Heart attack here. Tyler's here. All right, good deal. We're on in chapter 3 still. Application of differentiation, 3.9, we're just starting. That's differentials, and we're on page 235, example 1. By the way, this example 1, they also have at larsoncalculus.com for an interactive version of this type of example. So my question again is, what is C? Okay? C will be 0. This is the point, C, f of C. Okay? C was 0, f of C was 1. Okay? So, what is f prime of, and what's C? 0. What's f prime of C? 0. Cosine of 0. That's not a theta, that's a 0. Huh?
That's how you say it's the cosine of 0.
Wait just a second. Okay. Cosine of 0 is what? Anybody? Cosine of 0. Anyone? Think of the graph of the cosine function. 1, exactly. It's 1. All right, so your f prime of 0, or f prime of c, that is f prime of c, because c is equal to 0, that's 1 times x minus c. Okay? Pretty easy tangent line approximation. Y is equal to 1 plus x minus c. That's it. That's it. Okay? Now, it says, then use a table to compare the y values of your linear function, that's this one, linear function with those of alpha of x, which are there on the open interval containing x equals 0. Okay? Now, I'm not really wanting to fill in a table. I think they've probably done it for us, so let's take a look at what they've done. Let's erase my ink, and let's see what they did. Derivative of f is f prime. They got it pretty quickly, cosine x, okay? So the equation for the tangent line to the graph at there would be, and this is also the tangent line approximation, y is equal to f of 0 plus f prime of 0 times x minus 0. Oh my, I did it wrong, didn't I? I erased that. I put 1 there. Sorry about that. F of 0, I mean c is 0, and I put a 1 there. Sorry about that. But anyway, so what we have is y is equal to 1 plus x. That's all, not minus 1. I don't know where I put that came from. So it's 1 plus x. 1 plus x. That's it. Sorry, whatever I wrote was wrong. Okay, now let's do, here's the table. We're going to keep x's near 0. So we'll go from negative 0.5 to positive 0.5. These are pretty far away. Then we'll do negative 0.1, negative 0.01, positive 0.01, and positive 1. Those are much closer. So first, the function itself, you'll have to use a calculator. And you see this is your value of the actual function is 0.521 of the at 0.5, negative 0.5 at negative 0.1 is 0.9002, at negative 0.01 is 0.990002, at 0 is 1, that should be exact, and there you're 1.00999998, 1.09, and 1.479. Well, your linear approximation, really a lot easier to do. 1 minus this is 0.5. Look at that. Not too bad. First decimal place, exact. Second decimal place off a little bit. This one's 0.9. Okay, when you add 1 to negative 0.1, you get 0.9. Now you're good to 3 decimal places. Actually, 4 decimal places still around the 0.9. Here you're good to 1. No, actually 2 decimal places. Okay? Here we're good to 1, 2, 3, 4, 5, 6, 7 decimal places. You're still good. There you're exact. You should be. That's the point. Here you're good to how many decimal places? 1, 2, 3, 4, 5, 6, 7, 8 decimal places. Here you're good to all 4 that are listed there, 4 or 5, and there you're good to 2. Okay? Yeah, 2 decimal places. Pretty good linear approximation at that value. Now here's one reason that it's a pretty good linear approximation. The sine x is awfully close to a linear function near 0. So 1 plus that is going to be really, really close to it. Cosine x may not come quite as close, but it won't do too bad. Okay? And this is what I'm saying. Here is a graph of this function. F of x equal 1 plus sine x. Well, really, the sine x function would start down here and go like this, right? Okay? Down like this. Well, this is just a vertical shift, 1 unit up, and now it's like that. Okay? Like I was saying, your sine function near 0 is very close to a linear function anyway, so anywhere within here, you're going to have great estimated result. If this function is doing something very different, like having a lot of curvature there, it won't be as good. Like the cosine function looks more like this at 0 than this would, so that wouldn't be as good. But this is going to be a great approximation anywhere between those values. Okay? Very, very good approximation. All right. Any question? Linear approximation. What do they call it? Tangent line approximation, which is also called the linear approximation. Okay? Now, why were we doing that? We had almost done that before. Well, that's leading to what we talk about in differentials. This author in a lot of modern textbooks try to give you these off-the-wall things out here to guide your thinking to what they're going to talk about next. In my mind, let's just talk about it and then say, hey, see how it applies here. But they like to do it the other way. So when the tangent line to the graph of f at point C, f of C, I started off like about 3 or 4 slides ago. This is y is equal to f of c equals 1 prime of c. That's your tangent line approximation. That's the equation of a tangent line. Okay? When that's used as an approximation of the graph of f, the quantity x minus c is called the change in x. It's x. Change it a little bit. Okay? The change in x. You moved x a little bit right or left of c. That's your change of x. And quite often we call that delta x. Right? Going back to what we did before we did derivatives. Okay? Now, here's some function f. We don't know what kind of function it is. They didn't give it to us. Here's the point C. There's value f of c right there, the y value. That point is on the graph. F prime of c is the slope of that. So c plus delta x, which would be your little bit of a change in c. That's a pretty big change in c, because that's even greater than c was. But yeah, there it is. X plus delta x is over here. I mean c plus delta x. Here's c plus delta x. If delta x is this much, then it's here. Okay? Now, your approximation would be f prime of c times your delta x. This, remember, is your delta x, the x minus c. They said that right here. That's your x minus c. Now, in case that doesn't really ring a bell with you, saying, well, where did they get that? If you say, and let's write it down here, x minus c is equal to delta x. Okay? Well, let's solve that for okay. Another way of writing this would then be y is equal to f of c plus f prime of c times delta x, right? The change of c's, x minus c. Okay. On your graph, I don't see an x. I don't see, I see a c plus delta x. Well, let's see. What happens here if we add c to both sides? Then this becomes x is equal to c plus delta x. Well, there it is. That is your new x here. That's your x value. C plus delta x is your x value. Okay? So, when we're plugging this in, okay, ooh, did I skip a step here? I guess not. Okay. So when delta x is small, this c plus minus c is small. That looks pretty big here. Then you're evaluating at this value of x. That's your x now. Well, that value is c plus delta x. So you have f prime times delta x, this change here, okay? And this value up here is c plus delta x, that's your x value, comma, f of c plus delta x, there's your y value. So this is your f of c plus delta x. This is your f prime at c plus delta x. And you see this is the difference. There's your delta y here. The change of the actual y value from here to there. And this is your f prime of c delta x. And Nolan's here. Good deal. All right. Now, and since a couple more people have come in, we've lost some too. Let me say this again. We've only got about 2 weeks of class left and then the finals. And I still only have three research papers in. I only got 2 weekends left that you can work on a research paper. So, yeah.
I'm sorry for being late. What are we talking?
We're in 3.9 differentials. Yeah. Okay. And also, test 1, I'm missing, I think, I counted them up before, I think 5 test 1s and missing 7 test 2s. And I'm giving out test 3 today. So please, folks, if you haven't gotten most of those things in, you're running out of term and have a lot to do before the end of the term. So anyway, here, differentials. That's what we're talking about, 3.9. Okay? And there is the illustration of what we're talking about. See, your linear approximation isn't the same as your F value. It can't be. If F's a curve and this is a linear approximation, they're going to be a little bit of difference. This difference here is sort of the error in the linear approximation compared to the actual function. Okay, that's what we're going toward. So when the delta x is small, the change in y, which we'll call delta y, can be approximated this way. Your delta y is your f of c plus delta x, that's the actual value of f, minus f of c. Okay? Now let's show that again back here, which is approximately f prime of delta x. Okay? Here's your delta y, which is the change of this to that. Okay? And that's approximated by f prime of c delta x. Not the same, but approximated by. Okay? Pretty close. The approximation differs only by that much. Now, when the delta x is small, like down in here, this range, there's hardly any difference at all between the black line and the blue tangent line. They're so very close, it's hard to tell. When you get up here, you see a little bit of difference. About there, you see a considerable difference, but it's still not too bad of an approximation. Okay? That's what we call the tangent line approximation. The delta y is approximately f prime of c delta x. Not exact, approximate. For such an approximation, the quantity delta x is traditionally denoted by dx and is called the differential of x. Okay? Well, guess what the delta y would be called? The expression f prime of x dx is denoted by dy and is called the differential of y. Okay? Now, this is the part that gets to be a little squirrely. Okay? Here it is. Definition of differentials. Let y equal f of x represent a function that is differentiable on some open interval containing x. Okay? The differential of x, denoted by dx, is any non-zero number. So in other words, you can't have the dx being 0. It has to be a little bit off from what your x is. Okay? So the dx is any non-zero real number. Then the differential of y, denoted by dy, is dy is equal to f prime dx. Okay? Now, here's the part. I mean, it almost is like they're talking in circles. And they're not. It really has a meaning this way. But if you wrote f prime in Leibniz notation, what is f prime of x in Leibniz notation? Isn't that dy dx? That's the same thing, right? Now, I'm going to write that the other way. dy dx is equal to f prime of x, right? Now, this is what mathematicians do not usually ever want you to say. But to get from here to there, doesn't it look like you multiply both sides of the equation by dx, and you have dy is equal to f prime of x dx? That's what it looks like. Here's why you're not really doing that. This is not a division. That's not a division, that's an operator. Okay? But it came from the limit of a division. So it's not a far stretch that this is just simply a rewrite of your derivative. But this is in differential form. So what? Why does this matter? What's the next thing we're going to do after we finish differentiation? It's the second part of calculus.
Approximation.
Say again?
Approximation.
No, even beyond that. It's part of that. The second part of Cal 1 is integration. Yes, intervals. And that's exactly what you're doing here. Remember your integral, if you've done that before, integrate this, and that's exactly the integral if you want. Okay? So that's where they're heading with this. Though there are other applications of it too, but that's where we're going. In many types of applications, the differential of y can be used as an approximation to the change in y. That is, let your change of y, delta y, be approximately that differential of y, or the differential of y is approximately equal to L prime of x dx. It is equal to L prime of x delta x, but we'll approximate it with the L prime dx. Okay? That's where we're heading. Now, we already did example 1. It was pulling teeth. Now we're on page 236. Let's do example 2. Let f of y equal x squared. Find dy when x is equal to 1 and dx is equal to 0.01. Okay? All right. Okay. What are you going to need to do? Find dy when x is equal to 1 and dx is equal to 0.01. Say again?
Wouldn't it just be 2 since...
Say again?
Would it just be 2? Because if you did like dy, isn't that just the derivative of x squared?
Okay. Yeah. dy is equal to f prime. Okay. Okay. Let's just call it y prime, which is derivative, right? Yuck. Hit the wrong button. Okay. Y prime dx. Is that what you were saying? Say yeah.
Yeah.
Okay. No, really. Isn't that exactly what this is? It's f prime is what we're calling it here. Now we're calling it y prime. Same thing, right? Okay. So we're looking for this dy when x is equal to 1. Okay. But what we have to do is figure out what y prime is. So if y is equal to x squared, what is y prime?
Y prime equals 2x.
2x. Okay? So dy is equal to 2x dx. Now, ooh, here's Will. There you are. Well, my word. I already wrote you here because I put Whitney in your place. So now I got Whitney here. Though she's not here, she had to go to the Birmingham campus. All right. So it says find dy when x is equal to 1 and dx is equal to that. That's a pretty simple thing to do, isn't it? dy is equal to, what is 2x when x equal 1?
2.
Say again?
2.
2. Right? Okay. And your dx is 0.01. So this is 0.02. There's your dy then. Okay? Now it says compare that value with delta y for x equal 1 and delta x equal 0.01. Okay? Okay. Your y is equal to this, so they want to know what the change of y is, okay? And your delta y, I'm going to write this down, is basically y2 minus y1. It's a change in y, delta y, difference in y. Where your y1 was at this equal to 1, and y2 was when this is equal to a little bit beyond 1. In other words, when x is 1.01. So this will be y of 1 plus 0.01, that's your x plus delta x, minus y at x, okay, where x is equal to 1, okay. I'm sorry, I should write a 1 here. This is y of x up here, okay. That's what your difference in y is. So what is y of 1 plus 0.1 minus y of 1? How do you get y of 1 plus 0.1? Here's your y. You want that at 1 plus 0.1. 1.01. So what you do?
Why is it 1.01?
Because it says, compare this with delta y. Delta y is y2 minus y1, which is y at the second value minus y at the first value. Y at the first value is when x equals 1, okay? Y of 1. And the second value is x plus delta x. Your delta x is 0.01, x is 1, delta x is 0.01, so it's y of 1 plus 0.01, which is 1.01.
That's just delta y,
This is your delta y. This is the y2 minus y1.
And against the delta x, delta y, just trying to find delta y.
You're trying to find
I
out.
was just wondering with like the 1.10, what is the 1.01 word?
Okay. X plus delta x. 1 plus 0.01. Okay. That is your new value for what your x. Okay. Here's what you got, folks. You got a parabola here. You start at y is equal to 1, x equal 1, that gives you y is equal to 1. You should have already done that. Now you're moving a little bit beyond that. 1 plus 0.01. What is your new y value of that parabola at 1.01? 0.01 beyond where your original x was. So what do you got to do? Okay. What is your y of 1.01? How do you get that? Say again? Say again? Divide it? I thought you just plug it. This is y of x is equal to x squared. Right? So how are you going to figure out what y of 1.01 is? Square it. Okay, do it. 1.01 squared. Anybody? Anybody?
It's
Say again?
1.0201.
1.0201. Okay? Minus, and what is y of 1? Y of 1. I don't think you need your calculator for that one, but you can use it. 1. All right, good. And what's the difference in that? 0.0201. And what was your dy up here? 0.02. So they are not far off. Your dy, which is your 2x dx, that was 0.02. Your actual change of y was the difference in the x plus delta x, y of that minus y of x, and that was this. So the difference there is 1 part in 10,000, okay? Not far off, okay? All right, good deal, I think. Okay, now, let's clear all my scratch out of the way and see how they do it. Okay, because y is equal to f of x equal x squared, you have f prime being 2x, which we finally got, okay, and the differential y, which is the change of y, dy, is f prime of x dx, okay? And that dy, f prime of x, when x equals 1, is f prime of 1, which is 2 times 0.01, which is x, the delta x is 0.01. So the f prime of x dx is that. It's 2 times 0.01 is 0.02. And yes, we got that pretty, well, pulling just a few teeth, we got it. Now using the delta x of 0.01, which is the same as it's just changing the dx to delta x of 0.01. The change of y now is f of x plus delta x minus f of x. That's your change of y. Your uy minus your old y. Okay? But that's f of 1.01. This x plus delta x, 1 plus 0.01 minus f of x, which is just 1 still. And when you did that, it's 1.01 squared minus 1 squared, and that came out 0.0201. Compared with 0.02 was our dy, our delta y is 0.0201. Basically 1% error. Okay? This graph shows the geometric comparison of the dy and the delta y. Okay? Here's the f of x at 1. Okay? This is x squared at 1 is 1. Okay? They didn't show the rest of the parabola that's down here. Okay? Now, when you go over just 0.01, 1/100th of the space there, you're up here, and this is your linear approximation. Y is equal to 2x minus 1. Here is your actual function here, it's up here, and this is your dy here, and this is your delta y, and there's a difference between the two. Now, they didn't put the numbers in here, but that's what we were representing. Remember, we called this 2. That would have been 2.02 because of x plus 0.01. That would be 1.01 times 2 would be 2.02 minus 1 would be 1.02, okay? And this was 1.0201, so that then is the difference. Okay? That illustrates what we were just doing, the difference between the differential dy and the actual change of y, delta y. Okay. Now, that was example 2. They did do a table in the book which shows you closer and closer values, well actually further and further values away, and how you can get pretty far off if you have your delta y too great, okay, delta x too great, okay, and that leads to error propagation. So if you let x represent the measured value of a variable, and x plus delta x, the exact value goodness gracious, that's a weird way to express it. Let x represent the value of the variable. X plus delta x represent the exact value. Then delta x is the error in the measurement. Okay? X is the measured value, x plus delta x is the exact value, then delta x is the error that you did. Boy, if I could have said it, I would have phrased it x be the exact value and x plus delta x being the measured value, then delta x would be the error in the measurement. To me, that makes more sense saying it that way, but this is still true. Okay? It's a weird way of saying it. Finally, if the measured value x is used to compute another value f of x, okay, well, if your measurement's not quite the same as the exact, then the difference between f of x plus delta x, which is your exact value, and f of x, which is your measured value, that is your propagated error, okay? So in other words, if you have a little error in your measurement, how is it going to affect your calculation? Because no measurement is ever exact, okay? There's always some room for error there. And if you're using that measured value, you may be propagating an error. So the f of x plus delta x minus f of x is your delta y, which is your propagated error. Okay? Exact value minus the measured value, then that would be your change of y. And again, as a practitioner, I usually think this is the real value and this is the measured value, where that's your error in your measurement. So I usually think of this written in the opposite direction here. You still come up with the delta y. It's still the same value. Okay. So the measured value of a ball bearing is 0.7 inch, shown in this figure. There's what we call a micrometer. Measures close as you can read on the scale here. Okay. The measurement is correct to within 0.01 inches. So it's read as 0.7 inches, but your measurement is correct to 0.01 inch. Estimate the propagated error in the volume of that ball bearing. Okay? So in other words, let's just determine what is the equation for the volume of a sphere. V is equal to, anyone remember? Volume of a sphere? 4 thirds, what again?
4 thirds power radius cubed.
Cubed. Okay. Now, I was going to say this is really a little bizarre here. If you're using a micrometer to measure this, you're not measuring a radius, you're measuring a diameter. But they drew this as if it's measuring a radius. So they really, this is a made-up problem, because if you're reading the micrometer, you're reading the diameter. You're not reading the radius. You have to take half of it. So we'll do it the way they said, though this is rather bizarre. Okay, doesn't make a lot of difference, but it's just not a real physical problem. This is a calculus.
Say, Mr. saying that the tool is off by a little bit, and then you got to figure out.
Well, yeah, like I said, no measurement is ever exact. You can never tell if you're exactly on. I mean, did someone fudge a little? Is your micrometer properly calibrated? You just never know, if you've got an exact measurement. So let's just say that we are within 1/100th of an inch when you read that, which you don't read a radius of 0.7 inches. Say we read a diameter of 1.4 inches, and then you took the radius to be 0.7 inch, within 0.01 inch. Okay? So what is your actual volume of 0.7? That's your measured radius. So this is the measured volume. That would be 4/3 pi times 0.7 cubed. Someone punch that in your calculator and see what you get. Give me quite a few decimal places too. Someone, anybody? 4/3 pi 0.7 cubed.
I got 1.436.
1.436, is it all?
Keep going.
Keep going.
75504.
Okay. All right. Let's back up one slide just for a moment here. Yeah. Okay, that's what I thought it was. Okay. Your V, and what is the actual measurement? The measurement is correct to within 1/100th of an inch. Okay. Now, what we don't know is which side you're on. Are you short or long? But let's just do the long side. So that the actual would be 0.71. Okay. Okay, we're going to do it the way they did and do the measurement error as a plus. It could have been a minus, okay? They didn't say, but let's do it that way. And that would be 4/3 pi times 0.71 cubed. What you got? So 0.71 now rather than 0.7.
Yeah, 1.4992.
1.499 what?
214.
214. That it? Okay.
09.
0 what?
91.
91?
Yes.
Okay. All right. We don't need that many digits. And just for fun, we don't know whether that error, it says within 0.1 inches. It may be, it was short that. So let's punch that one in too. V of 0.069. That would be 4/3 pi times 0.69 cubed.
I got 1.376 0.55281.
Okay. Well, let's see what our error was. It was about 0.6 that way and about 0.6 that way. So our error was about 0.06. Okay? Our measurement error was only 0.01. But the propagated error, when we then use that slightly faulty measure, then our error became 0.06, or approximately that, around there. Okay? Both plus and minus. Pretty close to that. Okay, let's see how they did it. The formula for volume of a sphere is 4/3 pi r cubed. R is the radius of the sphere. So you can write radius equal 0.7. And here your it could be either minus 0.01 or plus 0.01. We don't know which. Okay? So to approximate the propagated error, okay. Now, that's what I kept going back looking for. They said the propagated error was this. But here they said estimate the propagated error. They didn't say using calculus, so I was actually calculating the propagated error. They said estimate the propagated error. Well, let's go back here. And your estimated error would be this. dy is equal to f prime dx. That is your estimated error now. Okay? So what we're going to go back, I don't know what this is doing, but it's doing a strange thing. Your v is equal to 4/3 pi r cubed. What is your v prime here?
That'd be 3. That'd be 4 pi r squared.
That is exactly what it is, which is rather bizarre in itself, okay? Because the volume of a cube is 4/3 pi r cubed, and the derivative of that happens to turn out being the surface area of a cube, which is really bizarre that that's the case, but it is, so it's all right. Okay. Now, our estimated propagated error will be dy, which is f prime, let's call it v prime of r, not x, dx. Okay? So this will be the dv. Let's not call it y. dv is equal to, and what you just said, 4 pi, and your r was trying to remember what the r was. Here it is. I'm sorry. On the wrong page here. 0.01. No. 0.7. Okay. 0.7 times your dx, which is 0.01. Okay? So the dv here, your estimated error here in volume would be 4/3 times 0.7 squared times 0.01. I don't know what I just wrote here. I said it's supposed to be a pi, and I wrote a 3, and I don't know where that came from. I said 4/3, and I meant to say 4 pi, and I guess that's where the 3 came from. So, if you'll punch this in, see what you get. The estimated propagated error, your change of volume, would be what? 4 times pi times 0.49 times 0.001. 4 times pi times 0.49 times 0.01. Anybody?
0.0615.
0.0615. I think that's enough, right? And what did we get before? We were approximately, if you actually did the subtraction here, which I didn't do, I was just estimating it, this would be, subtract this from that, and you get 0.063 or 62 something, and if you subtract this one from that one, you get a little different. So yeah, it comes out about 0.06. Your estimated 0.0618 or 15, I can't read, okay, and your estimated and your exact was either side of that, okay. Okay. So to approximate the propagated error, to approximate it, you take the derivative of that, 4 pi r squared, exactly what we did, write delta V, that's the exact error, is approximately equal to your dV, which is your estimated error, okay? And the estimated error was 4/3 pi r squared dr, which is 4/3 0.7 squared plus or minus 0.01, okay? They put in the plus or minus here. We hadn't before, but that's exactly what your error is. So that's plus or minus 0.06158 cubic inch. So the volume has been propagated error of about 0.06 cubic inch, which is what we got when we actually did the this. So that, oh, okay. Now they didn't say do this, but they're doing it, okay? It says, would you say that the propagated error in example 3, which was, where is it? There it is, 0.0615. Is that relatively large or small? The answer is best given in relative terms by comparing dV with V. So the ratio of your error to the actual. And that would be, and rather than putting the other, 4 pi r squared dr divided by 4/3 pi r cubed. And if you did that, the 4's cancel out, the pi's cancel out, and 2 of the r's cancel out, and you have a ratio of 1/3r. No, I'm sorry, 3/r. Okay. Yuck, that's ugly. Okay. Okay. Now, so that would be approximately, 3r dr, okay. 3 dr over r. So that would be approximately 3 times plus or minus 0.01, that's your error, over 0.7. And if you do that, that would be 0.03 over 0.7. And that then comes up, and this is a plus or minus up here, 0.0429. Okay? What does that give you? That is your corresponding percent error. Percent error is the actual error over the actual value. Okay? The error over the actual value. And that's given in a percent. I mean, it's given as a decimal number here, move the decimals in place, 4.29%. Okay. Your measurement error was, again, a fraction of that because it was 0.01 out of 0.7. So that would have been a little bit smaller than this. In fact, a third of what this is. So that would be your, this is your percent error. Okay. In doing actual measurements, you don't really go through all this stuff, but that's, you can usually have all the numbers down there. But these formulas are correct. Okay. Now, they're talking about calculating differentials. I swear I thought I brought my watch up, but I didn't. How are we doing on time?
We're doing good. We got about 8 minutes left.
Okay. You want to take a quick break? I think I could use one. And we'll come back to calculating differentials. On page 238, we initiate what we call calculating differentials. As if you thought we hadn't been doing it already, now we're going to be calculating differentials. Okay? Now, everything we did with derivatives, same thing holds for differentials. Okay? Each of the differentiation rules can be written in differential forms. Okay? So remember these formulas that we had before. If u and v are both differentiable functions of x, then some constant times du, or the derivative, the differential of cu is going to be c times the differential of u. Remember in derivatives we said the derivative of cu du is equal to c, okay? and the sum or difference. D of u plus or minus v is going to be du plus or minus dv. Before we said, well, usually we had an x in here or something like that. dcu dx would be c times du dx. Yeah, that's how we would have said it before. And this would have been d of u of x plus or minus v of x would be, the derivative of that with respect to x would be u dx plus or minus dv dx. We just had a dx in there. Product rule, same as before. D of uv is u dv plus v du. Same as we did before, product rule before. Quotient rule, d of u divided by v is low d high minus high d low over low low. Okay? Same thing as before, but now written as differentials as opposed to derivatives. Okay? Exactly the same principles. We're talking about the same thing, it's just that we're expressing it just slightly differently. So, here's example 4. Okay? Yeah. Okay, here's our function, x squared. What's the derivative of that function? 2x. Okay, dy dx is 2x. If we wrote it in differential form, what would that be? That's derivative form. Differentiable form would be again, mathematicians cringe when you say this. It's like multiplying both sides by dx.
So it'll be 2x dx.
dy is equal to 2x dx. Perfect. Okay? That's the only difference. You're doing the same thing. It's just you're writing this. That's the derivative form. This is the differential form. That's the best way of saying it. You don't say you're multiplying by dx, but in reality, that's what it feels like you're doing. Okay? This one. What is the derivative of that? First, you do what? You rewrite it. That's what?
1 over.
Write it as x to the 1/2. Right? Now take the derivative.
1 over 2x.
Okay, 1 over 2x to the 1/2, or 1 over the square root of 2x. Okay? It would be x to the 1/2, then 1/2 x to the minus 1/2, which would be 1 over 2 times x to the 1/2. Okay? Now, how would you write that same thing as a differential?
So it would be dx over 2 squared x.
Okay? This part would be exactly the same. You just move your dx over here. And they put it on top. You could have put it out here, either one. Okay? That's the only difference between derivatives and differential. You write this as it looks like a fractional form, but that's an operator. And then you undo the fraction and write 1 on each side. Okay? That's all they're getting at here. It's just what it is. Okay, what's this one? Y is equal to 2 sine x. What would be in derivative form?
2 cosine x.
2 cosine x. dy dx is equal to 2 cosine x. What would it be in differential form?
2 cosine x dx.
Exactly. dy is equal to 2 cosine x dx. Perfect. Really a simple process. This is nothing all that new. It's just you're splitting up the derivative to be a differential. That's all you're doing. Okay, this one. Load, what do we do there? Derivative form would be using what rule? Second? Not quite. That would be if it was cosine x squared or something like that. This is just a product rule. Now what would that give you? Derivative would be what? you've used it a lot. Either one of two ways you can do it. I don't care. What would it be?
Negative x.
Okay, negative x times sine x would be, yeah, there it is. Negative x sine x. The other part of the product rule would be, what you did was the first times the derivative of the second plus
Cosine x.
second plus cosine x. Perfect. Now, what would that be in differential form?
Negative x sine x plus cosine x times dx.
Okay, yeah. dy is equal to this thing right here. They put it in parentheses, which is fine, times dx. Just pull the dx from here and put it over there. I mean, that's not what you're doing. But in fact, that is what you're doing. I mean, that's what it looks like. Okay? Is there an e here? Yeah, one more. Okay? What is the derivative of that? Again, the first thing I would do is write this in another form. What form would you write it? Y is equal to? Second? X to the minus 1. Then you take a derivative of that and you get negative x to the minus 2, which is negative 1 over x squared. And then how would you write that in differential form?
Negative dx over x.
dy is equal to negative dx over x squared, or you could have written negative 1/2 negative 1 over x squared dx. You could write the dx out here or up there, either one. So differentials, same thing as a derivative, only you split the derivative, put one on one side and one on the other. Make sense? All right, so the notation in example 4 is called the Leibniz notation for derivatives and for differentials, named after the German mathematician Gottfried Wilhelm Leibniz, okay, whose picture is listed there. And by the way, I imagine you've heard this story before, but just in case you haven't, both Leibniz and Newton are credited with creating calculus, okay? It was Leibniz, however, who tried to broaden calculus by developing rules and formal notation. He often spent days choosing an appropriate notation for the new concept, okay? Newton was more of a physicist and he needed the calculus to do his physics, okay? So he developed it to do that. Now, it is well documented, he was well on his way to developing calculus, it seems like a decade or more along the way, but Newton was a perfectionist, and he did not want to put anything out there that he could be criticized for. Newton had some problems, probably stemming from his youth. He actually was a premature baby, but his dad had died a couple months before he was born, so he never knew his father. His mother, they didn't think he would live. He did. His mother remarried, and the new husband didn't really want anything to do with the old family, so he was sent to live with the grandmother. So he felt some rejection there. And then later he came back, and I think his stepfather died, and his mother wanted him to come back and run the farm. He wasn't very good as a farmer, okay? That wasn't his talent. Fortunately, he had an uncle or somebody who said, this kid, even though he seems to have failed a lot, he is really, really bright. Let me send him to college, to university. And he did. But even at the university, Newton was poor. I mean, dirt poor. So he basically had to work for the richer kids at school, polishing their shoes, serving their food, maybe preparing the food. I mean, he was sort of like a servant to them until he was in the classroom and he ate their lunch, okay, because he went beyond his professors. In fact, as soon as he finished with the head math guy at Cambridge University, he said, let me step aside so you can take my seat, because Newton went way beyond him. So Newton had a lot of insecurities, so he would not publish until he was absolutely sure it was right. So he actually sent stuff to others and said, what do you think of this? You know, does this look like this is, do you see any problems with this? And he sent it to Leibniz. And then the Leibniz, it looked like, picked up on it and decided to publish it first. Now, he changed notation, did lots of other things, but we have no record of what he had done that decade prior to when Newton was developing his, but he rushed out there and published it. Actually published a few things wrong, so that's why a huge controversy came up. Newton was convinced that Leibniz stole his idea, and Leibniz said, no, I was doing something completely separate, and he may have been, okay? No one will ever know. But that was a huge controversy for the rest of Leibniz's life. He actually was younger than Newton, but he died first, and then Newton lived on. Newton just didn't get along well with anyone. He was, again, carried a lot of baggage. But anyway, this is Leibniz notation, and he did a lot of things beyond. Newton was just developing a tool to do his physics. Leibniz, I think, did see a broader picture, perhaps, than Newton did. Okay, differentials can be used to approximate fractional values. We've already done that. If you haven't noticed already, f of x plus delta x is approximately equal to f of x plus dy, which is f of x plus f prime. That was that first linear approximation or tangential approximation that we did earlier, which is derived from this linear approximation. This is done directly from this. This is your delta y, is the difference between these two, and that's f of this minus f of that. Yeah, that's exactly what that's your dy, and the dy is that. Okay, so we're almost feels like you're running in circles here. The key to using this formula is to choose a value for x that makes the calculations easier. Okay? Didn't know that was the key, but that's what they say. So let's do this one. Use differentials to approximate the square root of 16.5. We just want an approximation to it. We don't want the exact values. Okay? So what would you say, choose your x? What's going to be an easy x to take a square root of that's pretty close to 16.5? 16, okay? So that will make your dx, let's call it dx, or delta x. I mean, they're the same. I get confused in their notation. What's your dx or delta x? 0.5, okay? So, we want to approximate this, so we want how do you phrase that? You want your y, which is, this is the formula we used before. Let me see if I can clean this up a little bit. Y is equal to, it's this formula right here, y is equal to f of x plus f prime dx. Okay? Now, what is your f of x here? It's square root of x. That's equal to square root of x. Okay? I'm going to write it as x to the 1/2. Okay? What's your f prime? 1/2 x to the negative 1/2. Okay? And what's your x? So, okay. So your y then is approximately y, let's see, I'm trying to keep the notation correct, and I'm not doing a great job of it. F of x plus f prime of x dx. That's what we're doing, okay? Now your y, that's your approximation, is equal, what was your f of x? If x is 16, square root of 16 is 4 plus, and your f prime from up here is 1 over 2 times the square root of 16 is 4 times your dx, which is 0.5. Okay, that's your delta x, or your dx. So this will be y is equal to 4 plus 1/8 of 0.5. So someone plug that in your calculator and see what you get. It shouldn't be too hard to do.
$4.06.
4.06, is that what you said?
0625.
0625? Okay. How about plugging in the square root of 16.5? Second?
4.062019.
Okay. I'd say it's not too bad. We're good to 4 digits here, 4 digits there. Pretty close. Okay? Now, if you didn't have the little old calculators and you had to do that by hand, this would be much easier to do. I don't know, I bet you none of you have ever done a square root by hand, have you? No one does that anymore. Back when I was in high school, we did, because we didn't have calculators back then. I saw my first calculator my sophomore year of college. Yeah, I was in a big lecture room of about 200 students in a physics class, 8 o'clock, probably fall term, first, when in walked these two guys with these things strapped to their waist. We had heard about them, but I'd never seen one. And two guys came in, these were rich kids, you knew they had to be, came in with these strapped to their waist. Now they had to sit near a plug because they didn't have them battery operated then. You had to have them plugged in. And they would add, subtract, multiply, and divide. It cost about $400. And you had to have them plugged into the wall.
This sounds like it was working.
Huh?
How big was it?
It was pretty good size. It was probably about that size and about that thick with a plug. Huh?
I thought they had calculators longer than that.
Yeah.
No.
Plus,
That was the very first. It was
this
a
is for
Hewlett Packard. Second.
I was saying this is for basic principles, right?
That's about all it would do. And now you get those as freebies. You know, someone will give those away. That'll do those things, and they're about this big.
Right.
In fact, so
I
it's.
guess they had to start from somewhere, because I was expecting like maybe exponents or something else, because just doing the 4 basic
That's
principles
about all they
again,
did.
need $400.
Now within a few years, they could do much more for much less. But the very first one I saw, that's all it would do. That's what I was told. I never got to touch one. I couldn't afford that. But anyway, there is example 7. Let's see how they did it. Okay. Using f of x equals square root of x. I came around to that, but I forgot to write that first thing. You write f of x plus delta x is approximately f of x plus f prime double x, f prime of x dx, which is the square root of x, that's your function, over, and then the derivative of that would be 1 over 2 times the square root of x. And there you choose your x equals 16, your dx equal 0.5, obtain the following approximation. The 4, square root of 16, plus 1 over 2 times 4, which is our 1/8 of 0.5, and that would be 4.0625. And compare that with, that's your approximated value, compare that with the actual value. Well, they don't do that. But here's basically what they're doing there. All right. Here is the function square root of x. Okay? Your actual value is on there, somewhere right around there, 16.5. We chose this one, and notice the tangent line. I can't tell the difference in the function and the tangent line until you get out here or down here somewhere. So this is going to be a very close approximation. And here's the linear approximation to it, and for value, well, wait. Trying to see. Oh, well, 1/8 x plus 2. Okay. The g of x, I'm still, oh yeah, okay, I'm sorry, that's the tangent line. That is the slope, that is the tangent line, okay. Here's your, not quite the slope. Yeah, it is. 1/8 x plus 2, that would be your tangent line. And you get that by plugging in. Okay. They did a lot of steps there before they got to that place. And so you see down here is a little bit of an error. Not as much here. So it's up here you get a little bit of an error. You see it deviating. But we're really very close there. And we're very, very close to our answer. Well, I'm not going to beat it to death, but, or maybe I am. Your f prime is at 4 is going to be it's going to be 1/8. So this is f prime at 4. Okay, and your tangent line is y minus 4 plus 1/8 times x minus 16. Okay, so that would be y, that's an equal sign. Y minus 4 is equal to 1/8 x minus 4. Add 4 to both. No, 1/2 of 16 is 2. I mean, 1/8 of 16 is 2. Add 4 to both sides, and you get y is equal to 1/8 x plus 2. That's where they got that, okay? That's where they got g of x is equal to 1/8 x plus 2. They skipped that part completely, and that's where that came from. All right, and that is the last slide here. However, that's not the last example, is it? Wait a minute. Sorry about this, folks.
It is the last example.
we skipped examples 5 and 6. Let's go back and do that, okay? Sorry about that. I wasn't paying attention. I think that's about the time I went on break and didn't realize I was doing that. Oh, no, it was a little before that. So let's do example 5, finding the differential of a composite function. So y is equal to f of x, which is equal to sine of 3x. Okay? Now we want the differential of that. So how do you think we're going to do this? Find the differential of that. Take a derivative. dy dx is equal to, help me. Say again? Say again? 3. I can't hear. Okay. Say that one more time. I don't think I understood you right.
I don't see where you're getting the 3 from.
Okay.
Sine 3x, but.
Okay. Well, I thought you said 3, so I'll take it out. Okay. So what's the derivative of that?
Cosine.
Cosine of what? Of 3x, is that what you said? Then you do the derivative of the inside, which is 3. Okay, so that's 3 cosine 3x. That's the derivative. Okay, so what's the differential? dy is equal 3 cosine 3x dx. Okay. Right. Okay? Make sense? All right. Let's do example 6. I think we can do it on the same page. Y is equal to f of x is equal to x squared plus 1 to the 1/2 power. What do you do first? What you do first?
What's it say y equals?
F of x. Okay, making fun of my writing. I understand. It doesn't hurt. I'm used to it. But yeah. Yeah. Okay, right.
Did you take the derivative?
Take a derivative. dy dx is equal to 1/2
times x squared plus 1 to the minus 1/2.
Okay. Times 2x. Very good. So clean that up just a little bit.
Could you maybe apply the times 2 to the 1/2?
Say again?
Could we put that 1/2 and multiply it against the 2x?
No. Okay. Number one, what I would do, the 2 in the denominator, 2 in the numerator, divide out. They go to 1. 2 over 2 is 1. Okay? Now this x is in the numerator. That is in the denominator. X squared plus 1 to the 1/2. That's how I would write it, just to get rid of the minus sign. You don't have to get rid of the minus exponent, but something looks a little better. So here's your dy dx. So let's write that in differential form. What would that be?
What are we doing?
Write it in differential form. That's what we were doing to begin with. Find the differential.
You must multiply by dx.
Yes, so that's what it looks like anyway. dy is equal to x dx over x squared plus 1 to the 1/2. You could have left that upstairs with a minus exponent if you wanted to, but they actually took it one step further, which I don't understand why, and said x dx over the square root of x squared plus 1. Now here's why I say I don't know why. The original problem was given in exponential notation, So why not leave the answer in exponential notation? They turned around and put it in radical notation. Well, to have this as an answer, I would have expected that to have been in radical notation to begin with. So it seemed like they overkilled on that one. But we got it. Okay. Either way you want to write it. And they actually wrote, and it doesn't matter here, I said this before, they wrote the dx on the outside. It doesn't matter. Fine, either way. All right, that did finally finish 3.9.
Before you go on, you
Yeah.
clarify something for me.
Okay.
How you say dx, x, why would that be wrong?
What's that?
I was saying, why is my answer wrong? Dx, x over x squared plus 1.
Okay. I guess there's nothing wrong about it, but usually we write the function times dx, okay? Rather than dx times the function, or dx over part of the function times another part of the function. It's just usually written as, here that would be capital F of x dx. That's just how it's done when you're integrating. You'll see that later. The last thing out there is your dx.
That makes sense.
It's more a tradition than there is any real reason for it. Okay. All right. So homework exercises on page 240 and following. Do either any of the odds 5 through 9. They're all three. Of course, the answers are in the back of the book. That's why I give you odds. But also at calcchat.com, they're worked out solutions, and number 7 is at calcview.com. Then do number 11, it's in the back of the book and at calcchat. Then do any of the odds 13 to 17. They're all at answers in the back at calcchat, and 13's at calcview. Do any of the odds 19 to 27. Those answers are in the back. They're at calcchat, and 23 is at calcview. Then do number 29 at the answers in the back and at calcchat. Do 31, the answers in the back and calcchat. Then do any of the odds 33 through, 41. Different application problems for this. Area, volume, stopping distances, pendula, projectile motion, lots of applications. Then do either 43, and those are all at calcchat. Any of the odds, either 43 or 45, they're both at calcchat. 43 is at calcview. You can do 47 if you want to give it a shot. It's in exploring a concept. Then true, false, either any of the odds 49 to 53, they should be at calcchat also. And that ends the chapter. There's some review exercises at the end. If you really want to do a few more, you can do any of the odds 1 through 7. They're all at calcchat. 9 or 11. Any of the odds 13 to 17. Do 19 if you choose. Any of the odds 21 to 25, 27 to 33, 35, 37 to 41, 43 to 47, 49, 51's a writing thing, so you can look at it if you want to. 53 is a modeling problem. You can look at that if you want to. We didn't do the infinities, so you don't need to do 55 to 63 unless you think that's going to be something you'll need in your major. Okay? 65 or 67, I think you can do any of the odds 69 to 77, and then there's some application type problems 79 through 87. And then using Newton's method, 89 or 91, and slight variation in Newton's method doing 93. Then what we did in the last section with differentials and other stuff, 95, 97, 99, and or 101. All at calcchat. All right, that finishes chapter 3. So before we do anything else, let me make sure I give you your test for chapter 3. Okay? let me all right, get out of here. Let's see where we are. We've still got a good 20 minutes to go. So let's get second.
10 minutes.
Oh no, I'm sorry, 10 minutes. You're right. I was thinking, okay, 10 minutes. Okay.
Once we start here, you may want to later, like postpone.
I hate this. I think we've got time to do, so I'm going to postpone, and then hopefully it'll. This is such a pain in the neck. Okay. All right. Let's move to 4.1. So chapter 4 is, well, if we can get it to open, is integration. You're right. I just can't get it to open. Now, there's only 5 sections. I doubt if we're going to finish all 5 sections, but let's get as far as we can, and we'll go from the current slide. Integration. Okay. Let's go back to grammar school at least. What's the first mathematical operation you ever learned?
2 plus 2.
Okay, you add it. Okay? And after you learned all those flashcards or however you did it back when you were in, and finally got addition down, you thought you were almost through, then what did they do? Then they turn around and had you undo it and did subtraction, which was the inverse operation of addition, though you probably didn't think of it in those terms then. But then when you finally got that done, all right, we got it knocked until they said, no, let's do multiplication. So then you had more flashcards or tables or whatever you had to do, and finally you got those pretty well, and right about the time you thought you were finished, division, which undid multiplication. And then probably a few years later, you finally got around to squaring a number, raising a number to a power, right? That was probably several years later. And then when you finally got a good understanding of that, what did you do? Okay, yeah, you raise it to a power. And then how did you undo raising to a power?
Rooted.
You rooted it, yeah. You rooted it out, yeah. You took square roots, cube roots, or whatever. So, all these are inverse operations of each other, okay? Later, I guess you have already learned to do exponentials, right? And then, how did you undo that?
Exponents. Negative exponents.
Logs. A log undoes an exponential, and an exponential undoes a log, okay? So for all your time in math, you've been doing first yin and then yang. You've been doing something and undoing something, okay? Well, guess what? Differentiation is one process, and what are we going to do now? Antiderivatives. We're going to undo that, and this is what integration is. Indefinite integration, okay? So what were our objectives here? To write the general solution of a differential equation. Why are we in differential equations? That's going to come much later. We'll use indefinite integral notation for antiderivatives. This is a little backwards from what most books do, but it makes good sense. You'll use basic integration rules to find antiderivatives, which again is a little backwards. They usually do antiderivatives and use integration rules, but it's okay, either way. And we'll find a particular solution for a differential equation, which is usually done in another course, but still we can do it. So again, they did all that as if you're starting with integration, but really you're going to start with antiderivatives. Now, what we're going to do is find some function, capital F. All before this, our functions have been little f's, haven't they? There's a reason for this. We want to find a function who we know the derivative is this, okay? This is the derivative. We want to find the function f whose derivative that is, okay? It says you might use your knowledge of derivatives to conclude that the only way you can get this to be the derivative is if your original function was that, right? Sort of backward thinking, okay? The function f, capital F, is said to be the antiderivative of the little f, okay? So a function capital F is an antiderivative of little f on some interval I when f prime, capital F prime, is the little f, for all the x's on that interval I, okay? So that's how we're going to start it, the antiderivative. You think, what function, if I take a derivative of it, will give me this function that's in front of it? Note that capital F is an antiderivative of little f rather than the antiderivative of, okay, there are articles of the things that make this. Capital F is called an antiderivative of f rather than the antiderivative of f. When I first read it, I said, what are they saying here? It's those little articles that make the difference. To see why, let's observe this. Say f1 was x cubed. Fine, that's what we just said. But let's do another x cubed minus 5. Take the derivative of this. What do you get?
3x squared.
3x squared. What? Take the derivative of this. What do you get?
3x squared.
3x squared. So they're both antiderivatives of 3x squared. Oh, how about this one? X cubed is, f3 is x cubed plus 97. What's this? 3x squared. They all have the same derivative, so therefore all of those are antiderivatives of 3x squared. So that's why we have to say an antiderivative rather than the antiderivative, because there's more than one. In fact, for any constant c, and this book uses capital C's for the constants, and most other books I've ever used have used little c's or something else. So if you're saying the antiderivative of the function, it's not even listed here, yeah, there, 3x squared, you say capital F of x is x cubed plus c, where c can be any constant in the world. Negative pi force, negative e over 15, whatever you want it to be. It's just some constant. Square root of 2/3, whatever. Okay. But then again, they still say an antiderivative of f. Okay. So theorem 4.1 says representative of antiderivatives. If f is an antiderivative, capital F is an antiderivative of little f on an interval I, then g is an antiderivative of f also on I, if and only if g is of the form capital F plus c for all x's in the I, where c is any arbitrary constant you want to put there. Okay? A weird way of saying it, but absolutely true. Okay? Using that theorem, you can represent the entire families of the antiderivatives of a function by adding a constant to a known antiderivative. That's what I was saying before, the antiderivative. So going back to that d sub x notation, this means the derivative with respect to x of this thing is 2x, right? You can represent the family of all antiderivatives of 2x, f of x equal 2x, by being g of x is equal to x squared plus c. You can call it capital F of x equal to x squared plus c. It can be anything you want to call it, okay? But you need the plus c there. This is the family of all antiderivatives of f of x equal to x. X squared plus c. Where c is any arbitrary constant at all, called the constant of integration, by the way. Okay? A family of functions represented by g is the general antiderivative of f, and g of x equal to x squared plus c is the general solution of the differential equation. Why they throw this in there now, I don't know. G prime of x is equal to 2x. Okay? Because what you could do is rewrite this as dg dx equal to 2x, and then take the differential equation x and y is an equation that involves x, y, and the derivatives of the y. For instance, y prime is equal to 3x, and y prime is equal to x squared plus 1, they're examples of differential equations. Okay. I'm going to say they aren't the same things. They're just examples of differential equations. And I don't know why they're introducing this now, but it's fine. So, find the general solution of that differential equation. All right?
Would it be
Y, you can say of x if you want to, is equal to?
I want to say it's going to be one half. Like it's 1/2 of x or x squared 2x.
At least that's a good start.
Yeah, sorry.
What? Something else.
2x.
General solution. Plus c. Okay? Now, really easy to check, isn't it? Take the derivative. Because that's what this is. This is the derivative of this, right? Take the derivative of this, what do you get? 2. That's exactly what that is. All right. There are going to be some rules to follow that make this far easier, and you don't have to think backwards and say, what function is there that I can take the derivative of to give me that? You know, there are going to be some much easier things to do, just like there were in derivatives, right? Got to be some rules that were easy to follow. Okay? Are we running out of time?
Yeah, simple again.
Okay. Let's just see how they did it. I don't see how they could have done much more, but let's just see what they did. To begin, you first need to find the function whose derivative is 2. One such function is y is equal to 2x. Oh yeah, that'll work. Now you can use theorem 4.1 to conclude that the general solution is y is equal to 2x plus c. All right, and the graphs of several functions of that would be here. 2x, this would be 2x, this would be 2x minus 1, this would be 2x plus 2, this would be 2x, you can just go on and on and on. There's a bunch of lines whose slope is derivative or 2. It's a whole family of curves. Okay? And that's where, let's see, where are we now? I wasn't following in the book too well. I think, okay, we'll start right here. Page 249 next time. Okay? Now, did we get enough to do any homework exercises? Probably just 1 or 2. Let's see. No, I don't think so. Let's not until we get a few more rules down. Okay, we'll begin there next time. So folks, please, I'll say it again, I said it early in the class and every time someone's come in, please don't forget about your research papers. A few of you, 3 of you have done those already, way to go, but most of you have not. That's like 12 have not, okay? First test, most of you have turned that in, 5 have not. Second test, most of you have barely gotten that done, 8 have, 7 have not. And then the third test you just got today. So not good to have a paper and 3 tests all sitting waiting to be done with less than 2 weeks left. Please get these done sooner rather than later. Good deal. Any questions? We'll continue with antiderivatives next time.